Okay. Sorry about that. Let's see. We were talking right here, right? So 2 is not an element of that set, and it makes sense why?
Yeah.
None of the objects inside this set are 2. Okay. And then some more things to help hit the point home. The set containing the set containing 1 is not the same thing as the set containing 1, is not the same thing as 1. Those are all very different things. Right?
Yes.
Make sense? Okay.
1 is in the set.
Yes.
Meaning your epsilon sign could apply.
Yeah, so I could say this is in this set and this is in this set. And that would be true. Although writing that epsilon backwards is weird. Yeah?
You want to give like a real life example of a set inside the set?
Like that?
Yeah.
What's wrong with that?
A real life one.
A real life one. So when we talk about a point on the plane, so when you talk about the point 1, 2 on your xy plane, the way we encode that is a set containing the set 1, comma, the set containing 1, 2. Notice that this is a set with 2 elements in it, 1 and 2. This is exactly how we encode this. So anytime you talk about the point 1, 2, you're really talking about the set containing 1 and the set containing 1, 2.
Okay.
Another way we might talk about it is kind of just classifying. I might say that the set of humans contains the set of boys and the set of girls. And those are 2 sets within the set of all humans. If I want, well, no, that doesn't quite work.
Why doesn't that work?
Because you just say boys and girls.
Because the set of all humans would be the set of all humans. Just because it just so happens that the set of boys is a subset of that doesn't work. So that doesn't quite work. So ignore that example, but this example works. And then just like this. Sets containing numbers. Real life. You're living it. And we just did it. We'll see more applications of this as we get to the next chapter. Okay. Some things to know. As a general rule, well, no, this is always the case. The set A is always equal to itself. And it's typically not the case that A is a member of itself. The reason that the author is doing this is to try and hammer home that equals and member are not the same thing. They're very different things.
What is an example where A is a member of itself?
Well, you can break logic, well, not logic, you can break your axiomatic system sometimes when you allow things like this, but one way I might say something that allows this is the set of all sets. It contains itself as a set. Okay. Another thing to note, for all x, if I say that x is a member of the set AB, what am I saying? I'm saying either x is equal to A or x is equal to B. When I'm saying that x is a member of the set 1, 2, 3, I'm saying x is equal to 1, or x is equal to 2, or x is equal to 3. Nothing weird there, right?
Why is it not and?
It just has to be one of them.
Oh,
X
so
either
and.
has to be A or X has to be B. For example, is A a member of this set?
Yeah.
Yeah, so X equals A makes this whole statement true. B, if X is equal to B, that also makes this whole statement true. X is equal to C makes the statement false, but C's not in it. So we want C to make that statement false. Good? Okay. As we were developing our logic, we would sometimes use the word property every now and then. A property of this, a property of that. And so the author comes back and says, really when you were talking about properties of things, you were talking about set membership. So an object is said to have a property if and only if it belongs to the set of things having that property. For example, when we say 6 is even, what do we mean? We mean 6 is in the set of all evens. When I say that chair is red, what am I saying? I'm saying that chair is in the set of all red things. So when we're specifying that something has a property, you can always think of that in terms of that object is a member of the set of all things that have that property.
Do you remember when we were doing identity? And you were saying that you can't use is in the grammatic sense always as equal?
Right.
Well, now our counterexample has become exactly what a property is. Because our counterexample was 6 is not even, or even does not equal 6.
Oh, yeah, you're exactly right. So is in this sense. 6 is even. Is now being used the same way that membership is being used. And that's something that we're going to get to, is that the language, you can't just rely on the words to dictate the logical interpretation, which we'll get to in just a second. But, so going back to when we talked about the identity of indiscernibles, we said that if x and y have all the exact same properties, then x is equal to y. That's what we said in chapter 5. Now we can say that in terms of sets. If y belongs to every set to which x belongs, then x is equal to y. And now we can do a really, really simple proof of this. X belongs to the set containing x, right?
Mm-hmm.
So, if y belongs to every set that x belongs to, then y belongs to the set containing x.
Okay.
Therefore, x is equal to
Why
y.
do you have not x?
Oh, that was just a mark. I was just proving this real quick.
Oh,
Just a little one-liner proof.
I thought we established that x is not typically in the set x.
No, that's not what we said.
Oh, A is the
A
set
does
is
not
in the
contain
set
itself
A.
as a set.
Right.
That's very strange for that to happen, and it only makes sense for that to happen in infinite cases.
Right.
Right. Make sense? Okay. Since Leah said so. So we good with this little mini proof on the fly? Not great, but I think it gets the point across.
Yeah.
Okay. So now we're moving on to subset. The way we read this is A is a subset of B. These are both sets. A is a subset of B. That's logically equivalent to. For all x, if x is in A, then x is in B. Or every element in A is also an element of B. Or something being an element of A implies it's an element of B. A is a subset of B. Make sense?
Mm-hmm.
So, as a general rule, not as a general rule, it's always the case, well, tell me true or false. A is a subset of A. Is that always the case?
Yes.
You sure?
Yes.
Okay, next one. If A is a subset of B and B is a subset of C, is A a subset of C?
Yes.
Yeah? What about if A is a subset of B? Is B a subset of A?
No.
No. And an example would be these sets right here. The set 1, 2 is a subset of the set 1, 2, 3. Right? Because everything in here is in here. But this is definitely not a subset of that.
Because 3 is not.
Okay. And then moving on to the point which Jacob noted is sometimes we use similar words or the same words in language and we mean very different things. Sometimes we mean identity, sometimes we mean as a subset of, sometimes we mean is a member of. And so look at example real quick. Trump is the U.S. president. What are we saying there?
The U.S.
Trump
president
and
is
US
Trump. It's
They're equal.
They're
Identity.
equal. Identity. Trump is identical with, probably should put current up there, the current U.S. president, right? Trump is a man. What are we saying there?
That
It's
is
a
a
subset of
property.
the set containing all men.
Trump is a subset of the set containing all men.
No.
He's an element of the set.
He is an element. Trump is a member of the set of all men. What do we mean by men or humans?
That's a property.
It's the same thing. Well, man is a subset of human.
Yeah, in that one we're saying men is a subset of humans.
Right.
Not men is in the set of humans.
Right.
Man is a subset of humans.
Everything that's a man is also a human. Everything in this set is in this set. Therefore, this set is a subset of this set. Maybe we should have did decide what these are. This is Trump equals president. This is Trump is in men. And then this is men are a subset of humans.
Okay, I'm getting a little confused on those two.
Okay, let's clear it up then.
So, why is men and not in the subset of humans? Why is it, or why is
What
men
is the set
not
of
an
all
element?
humans?
Everybody on there?
It's all the people.
Okay.
So Jacob is a member of that set.
Yeah, but so are men.
The set of all men is not one human,
Okay. Yeah.
right? Just like we have over here. Let's think about this set. Let's say 1 and 2 are guys and 3 is a girl, and there's only 3 people in existence. Okay, so we got boy, boy, girl, only people in existence, 1, 2, and 3. Trump happens to be 1. So Trump is a member of humans. And let's see, men in this case would just be 1, 2. So here's men, here's humans, and Trump's 1. So 1 is in here, and this is a subset of this.
Yeah.
Make sense?
Yeah.
Camera. For an example.
Yeah.
Okay. And then to help with the ambiguity in the language, let's look at 2 sentences. Socrates is a man. Men are mortal. Therefore, Socrates is mortal. Is there any problem with that logic?
Yes. No.
No. Let's try another one. Socrates is a man. Men are numerous. Therefore, Socrates is numerous.
False. Or there's something wrong with that.
Yeah, what's the problem with that?
Numerous is an adjective.
Men are numerous is not saying men equals numerous.
Was this saying men equals mortal?
No, it's saying men are a subset of things that are mortal.
Yeah, so here we were saying men are a subset of mortals.
That one we're saying men equals.
And we were saying right here, Socrates is in men. So Socrates is in men. Men is a subset of mortal, therefore Socrates is in mortals, right? Down here, we're saying Socrates is in men, same as before. But here we're saying men is in numerous. Of all the things that are numerous, men is one of those things. So numerous, here you go, Peter. Here's an example of a set that contains sets.
False.
Numerous is a set of all numerous sets.
Okay, that makes 0 sense. Why you're able to say men are mortal, yet men.
Men are mortal means
The set.
that everything that's a man is also a mortal.
Okay.
Everything in this set is in this set.
Saying men are numerous is saying everything that's a man
Is numerous?
is numerous.
That is not what it's saying.
That is literally
That is
what
what
that
it's
sentence is
saying, yeah.
saying. Men are numerous. All that is saying is if you are a man, you are numerous.
No, it's not. It's saying the class of men is a
Oh,
numerous
we're looking
class.
at it that way. I thought you were like applying an adjective to men. Like I'm a numerous.
The point is, the way that we interpret this changes drastically based off of what's here. All we did was switch mortal for numerous.
Wait, no, it still doesn't make sense to me then. The set of men are numerous.
Okay, just think about this.
Of
Is
all
it
numerous
true
things.
that men are numerous? Are there numerous men?
Yes.
So men are numerous. What does that mean? That means that there's many men.
Okay.
That means that the size of the class men is big.
Okay. Is it
You're
true
talking about the set of all men.
That, it's true that men are mortal.
It's true that men are mortal.
Okay, you're talking about the set of all men being mortal, therefore men.
No, when I say men are mortal, I'm not saying the set of men is mortal. I'm saying everything in the set of men, for each man in that set, they are mortal. When I say
you're saying the same thing.
men are mortal, I'm saying everything inside this set is mortal.
Okay.
When I say men are numerous, I'm saying this whole thing taken as a set is numerous. It's big. It's numerous. I'm not talking about the individual elements in there.
How do you know you're not talking about that?
Well, exactly. That's the point.
Is it interpretation?
There's ambiguity in our English language.
Okay. but-
Because I'm relying on my intuition for what men are numerous means.
Okay, what does that mean to you? Because like when I first read it, I was thinking.
That means that there are numerous men.
Okay, when I first read it, I was thinking like. I guess the way I was thinking of it is a stupid way to think of it. But like a trait applying to men, which is numerous. Like Levi's numerous.
Right, so you can't just rely on the structure of a sentence to determine what it's saying. Is the whole point of this example.
Yes.
And just changing one word drastically changes our interpretation of the sentence.
Men are numerous.
Make sense? How those are fundamentally saying different things? Yeah? Alright. So, there's a good little example with logic and language, or sets encoded in language. The English language, I don't know. That's a common case for other languages. Anyways, our next definition, proper subset. That's how we interpret this subset symbol without the line underneath. A is a proper subset of B, means that A is a subset of B, and A is not equal to B. So, 1, 2 is a subset of 1, 2, 3, but it's also a proper subset. However, if we had the set 1, 2, 3, is 1, 2, 3 a proper subset of 1, 2, 3?
No.
No, because they're equal. But is it a subset?
Yes.
Yes. So, proper subset, make sense?
Yeah.
Okay, so now just tell me true or false on each of these. If A is equal to B, where A, B, and C are always sets. If A is equal to B and B is equal to C, then A is equal to C.
Yes.
True.
True. If A is a member of B and B is a member of C, then A is a member of C.
True.
True, right?
No.
No! Let's do a quick example. Let's look at 1,
Oh,
the set
wait.
containing
No,
1,
that's dumb.
and the set containing 1 for A, B, and C. Now, A is in B and B is in C, but A is not in C.
Oh yeah.
Oh.
Sorry.
So now, this one does not work. Does it make sense why this one isn't universally
You
true?
got us on our toes.
Now notice there could still be cases where it is true, but
Mm.
we're not saying it's universally true that this is always the case.
Right.
Okay. Next one. If A is equal to B and B is in C, then A is in C. Same problem, right?
No.
No?
This one's
That works.
true.
Oh yeah, that one works.
God, you thought about that.
You thought about that one? Smart. Okay. If A is in B and B is a subset of C, then A is in C.
Yeah.
No.
Yes.
Yeah.
Couldn't there be something in B that A
Look.
is not a part of, and so A is not in
Which
C?
one were we looking at? This one?
Yeah.
In arrow where I'm looking at. A is in B, and everything that's in B is in C.
Therefore, A is in C.
Therefore, A is in C.
Okay.
Good? Yeah, it's just weird till it clicks and then it's like, duh. Okay, this one. A is a subset of B and B is in C implies A is in C.
Mm,
A is a subset of B.
You sure?
B is in very,
Sticking
very,
with the no?
very
Yes,
much
D.
false.
Huh?
it's literally the same thing as the second.
True or false? False?
Don't do this to
It's-
Donnie.
Are you thinking about this one? It'll probably help.
It's false.
It's false for sure.
It's false for sure?
For sure.
It's false. Example, let's look at the empty set. The set containing 1. And then the set containing 1. right? A is a subset of B, and B is in C, but A is not in C.
A is a subset of C or B? How could that be true?
The empty set is a subset of the set containing one. Is everything that's in here in here?
Yeah.
Can you find one thing in here that's not in here?
Oh, it's what's not false. What?
Then it's true.
Is that the logic?
Sure.
Yeah.
So,
Everything in there is in there.
didn't we already say that somewhere? The empty set's a subset of everything?
Yeah, we proved it a couple weeks ago.
A couple weeks ago.
Oh, I didn't put that up
It
here.
must have been last week because I.
Yeah, I
was gonna
remember us
say,
doing
how
it.
did we do
proved
it
it
a
in the
couple
past,
weeks
so
ago?
yeah.
Yeah,
I don't
we
think
talked
so.
about
I
it
am
in
not
the past.
introduced
I
to
gave
empty
myself
sets
a
yet.
so.
Okay,
Levi's like, yeah, just yes.
But we did it.
7 years ago.
we all good with this example? Anything weird?
Good.
Need to explain it again?
Okay, is a
Yeah.
Okay, so here's A, here's B, here's C.
Uh-huh.
A is a subset of B, or in other words, the empty set is a subset of the set containing one. That make sense? B's a member of C. The set containing one is inside the set containing the set containing one. Right? And then is A in C, is the empty set in here?
Yeah.
No. If I want to put the empty set in there, that would look like this. If we put it in there, okay, now the empty set's in there.
Remember what it means to be a subset.
Yeah.
Yeah, you're going to get confused by is a member of and is a subset. That's going to happen again and again. That's just life.
Okay.
So, this one now makes sense?
Mm-hmm.
Okay, last one. If A is in B and B is a subset of, a strict subset of C, then A is in C. For a
Yes.
strict subset,
Proper, right?
proper subset, oh yeah, another way to say it is strict.
Proper means they're not.
They're not equal.
They're not equal. Everything in B is in C.
Yeah.
And A's in B. Yes, of course.
Yeah, it still works. A is in B, and everything in B is still in C,
Mm-hmm.
Right.
therefore A is in C.
Right.
Couldn't trick us that.
Trying. Make it hard.
Your tone was really drum.
Alright, so some basic properties of the empty set. One, for all x, x is not in the empty set. That's what it means to be the empty set. Anything weird there?
What? Say that again.
For all x, for everything in our domain, it's not in the empty set.
That means it's something. What does that mean?
For any object you pick, it's not in the empty set.
Yep.
Oh,
For
okay, I
any
see.
x, doesn't matter what x is, it is not in the empty set.
Okay, yes, that makes sense.
Okay. Next one's kind of weird, but we'll say it anyways. There exists a set such that the empty set is a member of it, or in other words, we can have sets that have empty sets as members.
Yes.
Right?
For example, the set containing the empty set would be one such set.
Yes.
Good? And we can also have sets that don't contain the empty set. The set contains just one.
What? Why was that poor?
Next, for every set, the empty set is a subset of it.
Yes. So that's where we.
That's where we would say it. And yeah, that's an easy proof. X in the empty set, oops. X in the empty set implies X is in A. That is always true. Because X in the empty set is always false.
Right.
That's our definition of subset. If for everything here, if this implication is always true, then this set's a subset of this set.
Yeah.
Well, this implication is always true, therefore, this is always a subset of whatever set's over here, including the empty set, obviously. And then finally, for all A, for every set, if that says a subset of the empty set, then it's equal to the empty set. If everything in A is in the empty set, then A is the empty set,
Obviously.
because there's nothing in there.
Yeah.
And so the only way to make the implication false, or if we have this is A, and this is the empty set, right? We want A is a subset of the empty set. The only way to make this implication true if this is false is to make this false. So X can't be an A. That's another way to think about it. Good? Okay. So oftentimes we're interested in all the subsets of a particular set or the power set of a particular set. So let's make sure that we understand what it means to get all the subsets of a set. So let's look at the set 1, 2. The set containing 1, 2. What are all its subsets?
Set containing 1, 2.
Yeah, there's the easiest one.
Set containing 1.
Set containing 1, set containing 2, and then every set.
Yep.
Are there any other ones?
No.
Can't you have like the set containing 1, 1, and 2?
But those are equal.
Like that?
Yeah, it's not a subset.
Yeah, we just counted that right there.
Oh, I see what you're
That is equal to that is a subset of that, so we already counted that one. Any other ones?
That is it. That is all.
You can't think of any more?
No more
Becomes
exists.
obvious, Donnie.
Alright, no more. Okay, so yeah, those are all the subsets of this set. And we call the set of all subsets the power set. We'll come back and do more with the power set.
Wait. Proof by induction said it's the unison is that called power set? Unison.
Proof by induction?
Okay, never mind.
To
Keep
prove that a set is inductive, you prove that 0's in the set and that k in the set implies k plus 1's in the set.
Well, don't.
Induction is very much
Sorry,
tied to the
not
natural
proof by
numbers.
induction. The natural numbers is a subset of, or the inductive set. The natural numbers is a subset of all inductive sets or something like that.
Yes.
So it's a power set.
No.
The set of all inductive sets would. No.
It just happens to be in all those sets.
Yeah.
It's a subset of them. It's not a member of them. It's a subset of them.
Of all
Yeah. So take every inductive set, list out their power set, list out their set of all subsets. The natural numbers will always be in there. That's how you could say that if you wanted.
Okay.
With how we define the natural numbers in calculus. Okay. Moving on. Union. So the union. I should note, when we were talking about is a member of, equality, subset, and proper subset, we were always talking about relations on sets. These were giving us relations between those objects. X is a member of A is a relation. That's either true or false when you look at it. Now we're going to move on to union and intersection and difference. These are set operations. They take two sets and they spit out a set. So A union B, you can't call that true or false. It just gives you a set. A union B is just a set. But A is in the set B. That's talking about relation. You can call A is in the set B either true or false. Make sense what I'm saying? And the difference between relations and operators?
Yeah.
So intersection or union, now we're going to be talking about an operator. So for all X, X is in the set A union B if and only if X is in the set A or X is in the set B. So if X is in A or X is in B, then X is in A union B. Make sense?
Yeah. Isn't that just addition?
Kind of. Some authors, they use the plus sign for union, and they would call it set addition. Intersection. Similar idea. For all X, X is in the intersection of A and B, or A intersect B is one way you could read that, if and only if X is in A and X is in B. So it has to be in both of them if it's going to be in their intersection. One way that we sometimes think about these is, just clear some space over here. One way we sometimes think about these to help us with our intuition is to think about Venn diagrams. So if I have the Venn diagram, here's the set A, here's the set B. A union B would be all the stuff that's in either of them. So if we're thinking about points on the blackboard as my whole universe of objects, and A is all the points in here, and B is all the points in here, A union B is all the points that's either in A or B. Notice these points are in both A and B. You see what I'm saying? Similarly, A intersect B would just be this area right here. So this area right here, that's A intersect B, but this right here was A union B. Make sense of the difference?
Yeah.
Okay. So union, intersection. If A and B look something like this, what's their intersection?
Nothing. Empty set.
Empty set.
The empty set. The intersection of this with this, there are no points that are in this and this, right?
19 drop.
So when you have two sets such that their intersection is the empty set, we call those two sets mutually exclusive. So A and B are mutually exclusive if and only if their intersection is the empty set. Okay? Question. Is A and the empty set mutually exclusive? Are these two sets, forget what I have drawn up here, are A and the empty set mutually exclusive?
Yes.
Actually, yeah.
If A's not, yeah.
If
Yes.
A is not the empty set.
Even
Okay, what about this one?
Eight
Is
is
the
not.
empty set and the empty set mutually exclusive?
Yes.
You're telling me two equal sets are mutually exclusive?
Well, they don't contain
Yes.
each other.
Yes. Just look at the definition, don't overthink it. Is the empty set intersection the empty set and the empty set?
Yes.
Yeah. So they're mutually exclusive. I think our discrete
Oh,
math
yeah.
book specifies where A and B are not empty sets when we do mutually exclusive. But this author doesn't specify that. So with the way that he's defined it, the empty set is mutually exclusive with the empty set, which is kind of weird. Okay. And then set difference. Let's draw a picture of it real quick and then we'll go over the definition. Here's A, here's B. The set A minus B, that's all these points over here. That's everything in A that's not in B. A minus B is over here. B minus A are the points over here. B minus A. So A minus B and B minus A are two very different sets. A minus B is take A, now get rid of everything that's in B, that leaves the stuff over here. B minus A is take B, now get rid of everything that's in A, that leaves the points over here. See the difference intuitively?
Yeah.
And so now our definition for set difference is a set of all, or for every x, x is in the set A minus B, if and only if x is in A and it's not in B. So this point was in A minus B because it was in A and not in B. This point is not in A minus B because it is not in both A and not in B. It has to satisfy both those conditions. It has to be in A and it has to not be in B.
What does it mean to minus sets though, like in an actual numeric way?
In an actual numerical way to
Yeah.
minus sets.
Yeah.
I'm not sure what you mean by that.
Oh. Actually makes sense. What's not in one?
A minus B, take everything that's in A, now get rid of everything that's in B. That's A, take away everything that's in B. Okay. So some quick examples, make sure this is all making sense. Let's let A be the set 1, 2, B be the set 1, 3, 5, C be the set 2, 3, 5, 7. So C intersect A union B. Well, what is that? Let's look at what's A union B.
1, 2, 3, 5.
1, 2, 3, 5. A union B is everything in here or here. Is 1 in here or here? Yes. Is 2? Yes. Is 3? Yes. Is 5? Yes. And that's it. These are all the elements. 1, 2, 3, 5. Those are all the elements that are in A or B. We're rewriting A union B. That's 1, 2, 3, 5.
Yes.
You good with the first step here? All right. Now remember we were doing C intersect this. So C intersect we still have, but now let's look at C. C is 2, 3, 5, 7. What's 2, 3, 5, 7 intersect 1, 2, 3, 5?
2, 3, 5.
2, 3, 5. So does it make sense how when we intersect with C we end up here?
Yes.
Nothing weird there? All right, let's look at another one. Let's look at C minus B union A. So what's C minus B? C minus B, what do we have left?
2, 7.
Just 2 and 7. Now we need to union that with A, 1, 2. So 2, 7 union with 1, 2 is 1, 2, 7. Okay, let's do one more. Now notice here, all we did was move the parentheses. So going from here to here, all we did was shift the parentheses. Okay?
Okay.
And let's see how it comes out. So what's C intersect A? C intersect A,
1, or just
that's
2.
just 2, right? And then 2 union B is just 1, 2, 3, 5, right? 1, 2, 3, 5.
Yeah.
Notice that this and this are very different sets.
Is there an order of operations for set operations?
You have to have parentheses.
What if there's no parentheses?
It's a binary operation. Technically, it's not defined if you don't have parentheses.
Okay.
I don't know the natural order of precedence. It's not as natural to me as logic. I would guess that your precedence would be intersects, then minus, then ors.
Not just left to right. I mean, you could just do left to right.
No, not just left to right. But if there's any ambiguity, you put parentheses. I've never dealt with this not with parentheses. I don't think it's natural to have an order like we do with logic.
What again is the order for logic?
Logic?
Isn't it like it's or?
No, you do your nots first.
Right.
Or if you want to look at it backwards, so the last one you do is your ors, then you do your and, well, no, you can't think about it that way. You do your nots, then you do your ands, then you do your ors, then you do your implies, then you do your logical equivalent.
Makes sense.
Not and or implies logically equivalent.
Not and or implies logical equivalent, yeah.
Almost sounds like a sentence.
Oh, I'm getting off camera now. Oh no, we didn't finish it. Just randomly writing over there. Okay, so let's see, where were we? Oh, we did this. And then one more thing to note that we'll note again, so I didn't really need to note it there. A union the empty set is just
A.
And A intersect the empty set is?
The empty set.
Alright, so now move my camera over here and we'll continue.
You didn't finish domain of elements.
I'll catch that part. That wasn't caught on my camera before. Okay. So, that ends whatever section that ends. And then we move on to our next section. Now remember in our interpretation that we were always talking about some domain of individuals. So when you want to do an interpretation of a sentence, first you need to pick your domain, and then you need to pick operators and predicates that make sense in the domain that you're talking about, right? Well, similarly, when we're talking about sets, we often want to talk about the set of all the sets that we're talking about, our universe, in other words. Our universe of sets is what we commonly call it. So the domain of individuals, I'm always going to call our universe, and so I'm going to use a capital U to signify this in. What is this set? This is a set of all the sets that we're interested in.
Okay.
So in other words, for all x, x is in there. It's a set of everything that we're interested in. Make sense? It's our universe. So now we're going to come up with something similar to the negative sign. Negative A is going to be our universe minus A. It's everything that's not in A.
In discrete math, isn't it symbolized with a
And we call it the complement.
symbolized with a dash over the A, right?
Yeah, so this is how I'm going to symbolize it.
Oh.
I'm going to write it, instead of writing negative A, I'm going to write A with a line above it. And it's A's complement. So, we're over here now, so draw over here. So if this is our universe, and this is A, then A complement is everything that's not in A.
So
What's
is
a
it kind of,
complementary angle again? The two.
The complement, so the complement of 30 degrees is 60 degrees.
Right.
It's the
Nice.
angle you need such that when you put them together, you get a right angle. 60 degrees in Euclidean geometry. Okay. We were talking over here. So complement. So the complement of A, we're typically going to get it right like this, but as we're doing proof, sometimes we need to go back and write it as U minus A. The complement of A, it's everything in the universe that's not in A. Or it's a set of everything not in A is how we'll typically say it. So, quick example. If our universe of objects is a set 1, 2, 3, that's the universe that we care about, and A is a set 1, 2, and B is a set 2, 3, then the complement of the whole set A intersect B is our universe minus the set A intersect B. Our universe was 1, 2, 3. What's A intersect B?
2.
Just 2. So 1, 2, 3 minus 2 is 1, 3. So 1, 3 is a set of all objects that weren't in A intersect B. The complement of A intersect B is 1, 3. The complement of 2 is 1, 3. Make sense? See another example. The complement of A union B. Complement of A union B, that's U minus A union B. What's A union B? 1, 2, 3. So we have 1, 2, 3 minus 1, 2, 3 is the empty set. So 1, 2, 3 is the universe. Its complement is the empty set. Let me specify one more thing, and we'll write this one out. What if I had A complement union B complement? So before we had the complement of A union B, now we have the complement of A union the complement of B.
It's going to be 3, 1.
What is the complement of A?
It's going to be.
3.
It's going to be what the other one is.
What's the complement of B?
Those equal each other.
1. So 3 union 1 is equal to the set 1, 3, which was not the empty set. Very different sets. So the complement of A union the complement of B is not the same thing. This is not equal to A union B's complement.
Okay, but
Those are very different things.
is it equal to A intersect B complement? Because they ended up equaling the same thing.
A union B equal to...
intersect. Union A.
Oh, you're saying is this equal to this?
Yes.
Yeah, we'll get to that. That's logic. That's
On the other side of the word.
right here. 23, 24. That's just distributing knots across ands and ors.
That's
Not A or B is not A and not B. Yeah. Okay. So let's see what we were doing here. Proof. Proof that A union B is equal to B union A. So I'm going to show one way to do that and then show a faster way that we could have done it. So how do I show that two sets are equal? I need to show that everything in here is in here, and then that everything in here is in here. Right? So I'll start out with let X in A union B. And now I need to show that leads to X is in B union A, right?
Yeah.
But X is in A union B. What does that mean? That means X is in A or X is in B. What does that mean?
It means X is in B or X is in A.
X is in B or X is in A. And what does that mean?
I mean, X is in B, union A.
X is in B union A. Right?
Yeah.
So this implies this, implies this, implies this, implies this. Right? If I get rid of my let and I make all these back and forward arrows, then we're done. X is in A union B is logically equivalent to X is in A or X is in B is logically equivalent to X is in B or X is in A is logically equivalent to X is in B or A. Therefore, these two things are the same. I could have also just did a second line showing it the other way,
The other way?
right? Typically, you don't do it this way. You do it the other way.
Yeah.
What's the other way?
How I was doing it, I
Apply
say,
the other way.
Why?
let X that way and make all these implies.
That's how you prove it equals an identity.
Implies, 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 and then I would do 2, let X in
Right.
B union A, and show that that implies that X is in A union B, and then I would conclude, therefore, A union B is equal to B union A.
And is that, why is that so much better than doing the other way?
This is typically the way that you would show that two sets are equal.
Right.
We use just that back and forth arrow when we do that. We typically do it, how I'm going to do it down here, all in a line, same way we use equals, typically. But unless it is relatively short to do it, and you don't have to use any weird pieces of logic, it just logically follows, you typically do it this way rather than this way. But let's do another one. All right. So what are we going to prove here? We're going to prove that A minus A intersect B is just equal to A minus B. Okay?
That would make sense.
Right,
Wait.
yeah, that makes sense.
No.
But
What if
the
it's
thing about it with Venn diagram, it makes
Take A, get rid of everything in A and B, and you're left with everything that's in A and not in B. Let's do a Venn diagram real quick.
So B could still contain some A elements, or could have at the start.
Here's A, here's B. So let's look at this one, A minus A intersect B. So here's A intersect B, right?
Oh yeah, that's just A minus B.
A minus A intersect B just leaves you with this stuff.
Which is just A.
Everything over here, right? So now let's look at the other one. Now let's just look at A minus B. That's A minus everything in B, leaves you with everything over here. Same thing.
Everything in B that pertains to
Okay, so now let's prove it. If we have x's in A minus A intersect B, what does that mean? That means x is in this and not x is in this, right?
Okay, say that all again because you're saying, to be clear, you're saying x in A minus A. What does that dash mean right there?
X is in A minus A intersect B.
That means A intersect B is not in.
A intersect B is just some set C. X is in A minus C, whatever set that is. Make sense? Now, if X is in A minus B, or sorry, A minus A intersect B, what does that mean? It means X is in this and X is not in this. Right? So, X is in A and not, oh, I kind of did two in one go. Sorry. I should have a line above there. Let me just write it down here. I should have started with, that is logically equivalent to, X is in A and not X is in A intersect B.
I don't understand how that is logically equivalent.
X is in A minus A intersect B is saying that X is in the first set and is not the case that's in the second set.
Why is that?
So how did we do it over here? Where's difference? Oh, let me write it a simpler way. X is in A and X is not in A intersect B. There we go. That's exactly our definition of difference. X is in A minus B means X is in A and X is not in B. X is in A minus this thing means x is in the first thing and x is not in the second thing. X is in the first thing and x is not in the second thing.
So you're saying X is not in what B is containing, it's just the left side.
Right, if x is in A minus A intersect B, that's over here. X is in A and x is not in A intersect B. Just using this exact definition right here. So are we good with going from this to this?
Yeah.
Okay, now I just rewrote this the exact same way, except for if x is not in A intersect B, what does that mean?
It's not in A and it's not in B.
That means it's not in A and B, right?
Yeah.
So it is not the case that x is in A and x is in B. It's not in both.
Mm-hmm.
Right.
Good with this to this?
Yes.
Okay, now I think going down should be real simple. Distribute the not. Not alpha and beta is not alpha or not beta.
Right. And we know A, so we know not beta. What?
Well, we'll get there. We're just going to use simple tautologies. We don't even have to think it through. It's just going to happen. So are we good with this line to this line?
Yeah.
Okay. Now, distribution. Alpha and beta or gamma is alpha and beta or alpha and gamma. You good with this line to this line? Here, let me draw it out in simple symbols. If we have A, let's see, we're distributing and across the board. If we have A and B or C, that's the same thing as A and B or A and C. This is the same as this.
That's how and works?
Like Morgan's law.
Well, that makes sense.
I'm the teacher and I'm in here or outside means either I'm the teacher and I'm in here or I'm the teacher and I'm outside.
Okay.
Mm-hmm.
That makes
Going
sense.
way, way back. I don't know when we first did this.
I know.
Don't
That's
do it.
weird.
Don't do it.
Okay, so you see how this to this is using that same logic?
Yeah.
Okay. Now, x in A and x not in A is a
Contradiction.
contradiction. This is always false. This is always false. False or anything
It's true.
is just that thing, not true.
Yeah.
We're saying false or x is always equal to whatever x is. So I have false or this thing is always just equal to whatever that thing is. Make sense? Okay. So I have x in A and x not in B. Or x is in A minus B.
That was a very, very beat around the bush group.
Why?
Because it felt like you could have done it after line 1.
It is line 1.
Well, remember you need to go back to logic to prove it. So, like what we were doing up here, we're trying to prove that union is what?
Associated. Or
Commutative.
commutative.
And we prove that union is commutative by the fact that or is commutative.
Yeah.
That's the heart of the proof. So oftentimes the heart of these set proofs is going back to their logic equivalent. Distributing a not over A intersect B. Well, this one, it doesn't look the exact same, so not a great example, but we need to go back to getting our logic so that we have just logic and statements, and then we can manipulate the logic and statements till we get back to what we want.
Right, yeah, makes sense.
Yeah.
So you convert from sets to logical statements, manipulate it there, go back to your sets, you're done.
Mhm.
Which is typically how we prove these kinds of sets. Okay. So, and then at the very end, the author gives just a big list of useful properties on sets. So let's go over each of them and try and make sense of all of them, because they're things that you use over and over again anytime you're dealing with sets. So number one, A union the empty set is just A. Does that make sense?
Yeah.
B, or 2, A intersect the empty set is just the empty set. Make sense?
Yeah, we already did that.
Okay, A union B is the same thing as B union A.
We just did that right there.
A intersect B is the same as B intersect A. Does that make sense, or we need to see that?
That
Makes sense.
It's right there.
It's gonna be based on.
Everything in A and B is the same thing as everything in B and A. If it's in A and B, it's in B and A. We're using the fact that and is commutative to prove that one. Okay? The next one is, not exactly what we used in here, but we'd have to use a similar thing. So A union B intersect C is the same thing as A union B intersect A union C. Let's actually prove that one. One of you guys want to try that one? You're going to use the exact same property that we used in here. This distribution is a hard of it.
Can you use Venn diagram as proof, or do you?
You can.
Just
I don't
because
recommend
like,
that, but
isn't that would kind of be how Euclid did it? Is he focused a lot on pictures?
we wouldn't say Venn diagrams, but yes, his proofs were very pictorial, and there were things that we often assume from his proofs that were actually kind of a pain for us to prove in geometry. Like, I don't know what they all were, but one of them was probably something like, just because I have a circle and some angle bisect, or if I have some angle on a circle, how do I know that the bisector of the angle intersects the circle, or something like that? It's like, how am I guaranteed that that point exists?
Right.
And so we often in our geometry, we're having a hard time coming up with ways to do stuff like that. Maybe that one's simple, I don't know off the fly, but.
Doesn't that seem simple if you have a diagram to do it with?
The diagram helps your intuition.
But it
Yeah.
doesn't prove it.
It doesn't help you prove it.
Really?
That doesn't show you that that's a logical, it might help convince you that you should be able to prove it. But the proof of all geometric proofs should be able to be done completely independent of a diagram.
Yeah.
That is not the case with Euclidean geometry.
That's
He's
what I'm
very
saying.
much building a construction of a diagram with the way that Euclid did. He very much relied on
geometry
picture.
without a diagram. Why?
Geometry, you have your axioms, and you determine their logical applications. The exact same way we did proofs in this class. There's no difference. It's just that they're geometric proofs. And there's pictures that help you think about it. The same way that thinking about a Venn diagram would help us prove these things.
Right.
But a Venn diagram isn't a rigorous proof.
Right.
And so you might draw a Venn diagram, it might convince you, I should be able to prove that, but who knows, your intuition could just be way off. Never trust your intuition. Well, I should say that, not never trust it.
Shouldn't.
But
Yeah,
Never
rely
rely on it.
completely on it.
yeah, it's not perfect. My favorite example is Ramanujan. You ever heard of him?
For his name. Didn't you mention him before?
Ramen noodles, if you meant.
No. He was a genius mathematician from India. He had relatively little formal education that he could come across, and yet was just developing these theorems. Some English guy found out about him, took him over to England to start working. Anyways, Ramanujan, he hated proving stuff. He wanted to just use what he already knew because it was obvious to him.
Right.
And even he thought that there were some things that were obviously true that
You didn't know how to prove it.
one of the people he was working with gave him a counterexample to show that one of the things he thought was so obviously true was true. So he thought it was very tedious having to come up with proofs for everything that he was doing.
His whole life changed, probably.
The other example for those of you who took calculus, Leibniz had in his journal for, I can't remember how long, but something like 3 days, that obviously the derivative of a product is a product of the derivative.
Right.
Which, if you know the product rule, that is not the case. Those are very different things. And so,
Why did you think that was well, never mind.
when you're developing a field for the first time, if something just might appeal to your intuition and you're moving on with your life, and then it's like, actually that doesn't work. So, I mean, he never published like that. It's just we have it as a note in his journal or somehow that we found out that he thought it for like 3 days. No, that's nothing. But
Like
Done.
3 days.
even the great Leibniz, if his intuition could be so wrong, so can yours.
That's why I'm so much smarter than him.
Okay. Anyways, so let's prove number 5. Someone want to prove it?
I thought about it, but
I mean, I can give it a shot, there's no guarantees here.
Try it. It's almost identical to what we did here.
Okay, I'm not even gonna think about it.
Well, you can already see, if you think about unions like ors and intersections like ands, you're distributing an or across an and.
Okay.
So you should be able to see what's going to be at the heart of the proof just looking at that. Right? The logic at the heart.
so it's gonna be A and B or C. But you're gonna want to.
And you can just use set builder notation if you
let
want.
X in.
Is everyone okay with set builder notation?
Is that what?
Set builder notation?
Do I need to use it for this proof?
Like what you've been using
Never
this
mind.
whole time?
No, I haven't been using it. Never mind. Keep going.
I don't need it, do I?
No, I just prefer to write that way. I hate writing it this way, but if you guys like it this way, just never mind.
Well, it's not
You're
in
gonna go- No, you're gonna do A intersect or union B.
You're doing 5.
Ah, 5.
What were you looking at?
The wrong one.
A union B intersect C.
Ah.
So how I think you do it is
Intersects A and C.
Man, this is just like third week of discrete math.
let X
Yep.
in.
This is the exact proof in discrete math. It's going to be on next week's homework, so.
Literally. So.
Sounds fun. See?
Are you in discrete?
Yeah, we're
Yeah.
the last 3 are in discrete.
All my best students take discrete, Jacob.
Hey, those are great ones.
Because you're gonna take trig.
No, dump train.
You dubbed trig.
Down in the trash.
He's gonna take
I
both.
don't know about trash, but hey.
He wants
This
business
counts as a.
Oh yeah, that's how MIM avoided.
This class?
No. Discrete.
No, it's just an elective.
It's math.
That's what I thought it was at the very beginning.
No, it's a math class. But you should still take trig and calculus next year if you can. Just a common sense thing to do.
So why doesn't? Yeah, never mind. That's another question.
Definitely I'd take trig for college.
Oh wow.
Are you stupid?
He's already going to take discrete math. He'll be more than prepared.
No, you won't. You're wrong.
I'm not prepared.
You're wrong.
You did both.
Yeah. I just bring that through everything. Still stuck on proof by induction.
X is in A
Why did-
or
why did
X
your
is in
calculus
B
class have that?
intersect C.
After you need both of those classes.
Need your X is in. You're going to be 2
Oh,
separate
yeah,
stages.
yeah.
And that's going to help you.
Yeah, it is. Why did your calculus class have such a hard time with proof by induction?
Dude, I did trig and discrete math.
My calculus class had never done induction, and there was no soft introduction to it like there is in discrete math.
No soft introduction. What was our soft introduction?
Proof by smallest counterexample.
So you think that maybe helped set us up for it and they just had got thrown into it?
Yeah. Oh, for sure. You'll see how fast we just suddenly are doing it. We'll just be 1 second talking about inductive sets. The next thing you know, you're proving things are inductive. It's very fast paced.
In his class with the other.
You had class already.
Yeah.
So discrete math at 2. Don't worry.
Yeah. I got up there, told him my mission of the world, and he basically
Why? Why?
Yeah.
Why, Peter? Why?
F'd me up.
X is in B,
Why are you
and
saying this, right?
X is in C.
Why is
Oh, yeah, that is right.
Yeah.
Just don't lose your parentheses.
Why your toes on your feet?
It hurt me. It hurt me like my soul. I was like you heard?
Okay.
Last year we did that test. I felt like it was ridiculous.
I started talking about God, and then everybody got up and started talking about God.
Yeah, that's what I was thinking. Why are you in the cabin? Because I believe in this word.
Why do you believe in this word? I believe in God. Why do you believe in God, bro?
Yeah.
Then you can do and or.
Remember, X and A, X and B, X and C, those are just statements. you can just view those as alpha, beta, gamma. So you're doing alpha or beta and gamma.
So that's right.
Yep. Oh, no.
No?
No.
Are these supposed to be switched?
Yeah, sorry.
Yeah, so that's where you're going.
So I have a question, why is it X instead of for all of X?
Well,
We could put the for all in front,
X
but
was guessed.
that becomes tedious.
Okay.
So when we do say
It's just-
that, we're saying for all x, where x is in
A.
Donnie, is gamma the third letter in the Greek alphabet?
Why'd
Why'd you say alpha, beta, gamma?
I don't know. I'm guessing it is just because I
I
said
think
that's
it
what
is actually, yeah.
What does the gamma look like?
Kind of like a y.
Yeah, I see
You see, they got A, B, Y, we got A, B, C's.
that. I actually just read.
We see
I
their
I
Y.
used to live in the time of Greece.
Alpha, beta, gamma, delta. That sounds right.
He's like, yeah, why?
Alpha, beta, gamma.
Oh.
I'm just barely got to the story of Greece in that series.
You're taking forever.
Well, it's because I got a new phone and I didn't get my mom's Audible. But yeah, so I gotta learn about the explosion of ideas.
Didn't Greece start from the ice giant? Or is that wrong?
Oh, that's, Norse mythology.
Norse mythology.
I have no clue what that is, so.
I know that
Norse mythology sounds like a solid guess.
Greek schemes.
It
No,
is
I
actually
just because I read the book.
It's a pretty solid.
Oh, you actually know the mythology?
Yeah.
Yeah.
Roman mythology goes back to Troy. And so Romans claim that they're the descendants of the people of Troy.
But the people of
As
Troy
in Troy
were
that
native
got
people
conquered by the Greeks.
over and over.
So the mythology says.
That Troy got conquered by the Greeks got conquered by the Persians.
No.
Someone got conquered by the Persians.
The Persians got conquered by the Macedonians, which were very Greek. People call Alexander the Great a Greek, even though he's a Macedonian.
You're referring to like the 300.
No.
Like,
He's referring to Alexander. I assume you're Alexander the Great.
300 Sparta.
Most people call him Greek, and he conquered all of Persia.
Yeah, the Persians.
That's what he did. That's what he's famous for.
Did Persia not conquer Greece?
No,
They
they
tried.
lost the Greco-Persian Wars. Persia lost. Greece won.
Oh, they lost
Both of
that.
them.
Both of them? I thought the Persians won one of them.
They
Nope.
basically- their army
They
got
lost
beat
at Marathon.
and died out.
They won the Battle of Thermopylae, but they lost the Battle of Salamis, and they lost the Battle of
That's right.
Marathon, and they lost the Battle of Plataea.
Well, I haven't got to their destruction is.
You said history of Greece?
Just, yeah.
Okay, anything wrong with that proof?
Yeah, check me, make sure I'm good here.
I did have a question. So, on the first line, there's X in B intersects C, and then on the next line, X in just like disappears.
Try that.
It's just my poor
No.
handwriting.
Here.
No, what you pointed to before, that's in there because that's the definition of B intersects C.
Mm-hmm.
I'm saying the second one to the right of the parentheses in the first line. To the left, sorry.
A.
Can I just...
Yeah. I'm lost by what you're saying.
Okay, so I see that this equals this. I'm just
Uh-huh.
wondering where this went, right there.
It is distributed.
X in B and C.
Okay, but B and C is that, according to whatever definition you have over there, isn't it?
Let's see. B intersects C. X in B intersects C is logically equivalent to X in A
Oh.
and X in B.
Okay, I see.
Any other questions? What?
I mean, no. Usually say, are you good? Yes. You understand?
Pretty arrogant of you.
Arrogant?
Are you good?
I don't know.
that's a perfect proof of that. The proof of 6 is basically the same. Let's continue through these properties, make sure that they make sense. A union everything not in A union A complement is the universe. If you take everything that's in A and you take everything that's not in A and you union them together, you've got everything.
What's the answer? Not 6 or 6.
Exactly. So this one makes sense? Alright, this one. A intersect the complement of A. In other words, if we take everything that's in A and everything that's not in A, then we've got nothing. There's nothing that's in A and not in A.
Wouldn't the empty set be in A?
No.
It's a subset.
If the empty set's in A, then the empty set's not in A.
Yo.
Or, sorry, if the empty set's in A, then the empty set is not in A complement, is what I meant to say. Sorry about that. Let me finish my sentence. This line makes sense?
Yeah.
Okay, next one. A union the universe is just the universe.
Right.
That one makes sense?
Universe.
Set of everything that we care about.
See, that was the biggest thing that confused me when you talked.
It's the domain of individuals, whatever that is. If you're in psychology, you might be all people. And maybe A is people with dementia, in which case A complement is people that don't have dementia. So we're good there, good there. A intersect the universe is just A. That one makes sense? If we take everything that's both in A and the universe, then we're just left with everything that's in A.
Right? Because A is in the universe.
Gotcha.
If they have to be in A and in the universe, then that's the same as they just have to be in A. Make sense?
Yeah.
This before all these we have for all x in or what? What? I'm confused why you say if it's just if it's in A. If A and
Well, what does it mean for sets to be equal? It means everything in here is in here and everything in here is in here.
yes.
That's what we mean by they're equal.
So A.
So if I'm talking about everything that's in A and the universe, that's the same thing as talking about everything that's in A. Look, if the universe is objects in the universe and A is the objects in this room, then the set of everything that's in this room and in the universe is the same thing as everything that's in this room. Name one object that's in this universe and in this room that's not in this room.
Okay. Okay. Thank you.
Or the other way, name one object that's in this room that's not in this room and in the universe.
Challenge.
Good? Where were we? This one. Make sense? You just can't hide your face. I can still see you.
I'm trying to think.
Learn the rules of peekaboo?
Yes.
Okay. Next line. A union A is just A. Union a set with itself, you still just have the same set.
Yeah.
Intersect a set with itself, you still just have the same set.
Yeah, but
The universe is not the empty set. Whatever your universe is, it is not the empty set. This one's kind of harkens way, way back to when we were doing interpretation. When we did interpretation, our domain of individuals had to be a non-empty set. We required that to be the case. The reason we required that to be the case is we always wanted to be able to deduce from a statement like for all x, u of x, where u is some predicate about x, we could always go from this to this.
Right.
And that required our domain to not be empty. So whatever our universe is, it can't be the empty set.
Because we need something in the set, right?
Our domain always has something. Next one, the complement of the complement is just the set itself.
negative.
Can you do
Yeah,
that?
double negatives.
I know it makes like intuitive sense, but for some reason I always struggle with groups like that. Can you demonstrate the group?
Yep. So, X is in A implies X is not in A complement implies X is in A complement.
Ooh, done. Crazy. Fast.
Alright, next one, that one looks kind of like a contrapositive. If A is equal to B's complement, then B is equal to A's complement. That one make sense?
I'm thinking angles every time.
Nothing to do with angles. Does it make sense that if A is equal to the complement of B, then B is equal to the complement of A?
A is everything that's not.
We could do a quick proof of that one. It's not hard, so if it's weird, we can always just prove it. So, which one were we doing? 15, thank you. So I'm going to use this fact to prove that this is the case. How am I going to prove that B is equal to A complement? I'm going to show that everything in here is in here, and then everything in here is in here. I'll just do it one way, and I think you'll see it. So I start out with X in B. If X is in B, what does that mean? That means X is not in B complement. Since B complement is equal to A complement, that means X is not in A complement. And since X, sorry,
Wait a minute.
X is not in, oh, oops.
Yeah.
A, there we go. B complement is equal to A. I'm assuming my antecedent is true. So I'm assuming A equals B complement, and I'm proving the right-hand side, right?
Okay.
So if X is in B, X is not in B complement, which means X is not in A, which means X is in A complement.
B equals A complement.
And then, yeah.
So everything in B is in A complement, and then you can do the same thing to show everything in A complement is in B. Make sense, or do we need to see it?
Good.
Makes sense.
My biggest dilemma here is a complement. We go over what a complement is again exactly because it's not just everything not in B.
Oh, you want to write it out like that? It is everything not in B, but we can write it with the U if you want.
Would please.
So, let's see. So we start out with X is in B. What does that mean? That means X is not in U minus B.
Right.
Which, I mean, I need to use my definition real quick to use my equality. I need to use this equality somehow. I don't know how you're most comfortable with that. Are you good with just going like this? Therefore, X is not in B complement. Can I do that now?
Not in, you need to cross it.
Oh, thank you. This is the definition of B complement,
Yes.
right? And now I know B complement is equal to A.
Yes.
So X is not in A,
Yes.
which gives me X is in U, and X is not in A, because X is always in U, and X is not in A,
That means X is in.
which gives me X is in U minus A. It's in U, and it's not in A, so it's in U minus A, which gives me X is in A complement. I mean, you could spell it out more if you want, but it's going to be that same thinking. You good? All right.
So is that,
Go ahead.
an if and only if, or is it just an implies? So
15?
Yeah.
It's just an implication, but doesn't
Can it
matter.
be if and only if?
Yeah, because it says the same thing.
It's just the exact same proof backwards.
Well, just change your name of A and B, and it's the same thing. It's just a renaming.
Yeah.
Okay. 16. If A union B is not the empty set, then one of those two sets was not the empty set.
Makes perfect sense.
And the way you would probably prove that is contrapositive.
Mm-hmm. Saying there is or.
Saying not this implies not that.
Right.
So in other words, if A equals the empty set and B equals the empty set, then A union B is the empty set.
Right, perfect.
And that's how you prove it.
Which makes total sense.
Next, if A intersect B is not the empty set, then A is not the empty set.
But also B.
Also, B is not the empty set. But you could get that just by switching the order.
Yeah.
Good on 17?
Wait. Yes.
18 is just saying that union is associative, and you would prove this using the fact that OR is associative. Does that make sense how you do this one? And then AND, or intersect is associative. You just use the fact that AND is associative to prove this one. Good? Alright. What about A union A intersect B? Let's look at a Venn diagram for that one, and then we can prove it if you want. But maybe a Venn diagram will make it obvious enough for you. So, what number was I looking at?
20.
20. So we have A and B. So here's A, here's B. And we're saying that
Is that all?
Then.
What does she mean?
I think she just said
so A union A intersect B is just A.
Is that supposed to be an intersect?
Oh, yes, thank you. So this middle part right here is the intersection, right? This part is A intersect B. So A union A intersect B is still just A.
perfect.
Does that one make good sense, or do we need proof?
That's great.
Sense?
Next one, A intersect A union B is just A. So, now, A union B is all the stuff out here, right? So A union B is everything out here. So if we do A intersect A union B, that's just A. Probably helps to think about in the other order. A union B intersect A is just A.
Yeah.
That would make sense? Okay, was that 21? 22. A complement is not equal to A.
Where?
Seems pretty obvious. The definition is exactly that.
The only reason that that works is because the universe is not the empty set,
Yeah.
right? So if we're in a one set universe, if we're in a universe where there's only one object, then either that object's in A or it's in A complement. And that's the smallest universe that we can have. Let's look at the next one. So the next one's how you distribute nots over OR. So
Right.
the complement of A union B is the complement of A and the complement of B. Maybe this is one where it's worth, well, didn't we do this one?
Yeah, we did. Well, some very similar.
No, we did it.
Sort of.
We did it. Right.
We said this
basically
was
did it.
so, but we didn't really prove that it was.
We didn't prove it?
Yeah.
So maybe we'll see one of these distributing the
We
complements.
did it right there. It's half erased.
Oh, I erased it? We'll just write it out real quick. So if X is in, let's see, we're doing 23. If X is in the complement of A union B, that's logically equivalent to X is not in A union B, not in, right?
Yes.
Yeah.
And that's logically equivalent to
X is not A and X is not B.
if X is not in A union B, then that's the same thing as X is not in A, and X, well, maybe we're skipping the heart of the problem there. So let's not do it that way. So it is, how do I want to say this?
You could change it to be not X is in A union B.
Can I pull a not out over there?
You can put,
Is that that how I did it? Or did I do another step? Is this too much? Not x in A or x in B. I think that's the next most logical step to
Like
take.
2 steps in one, isn't it?
Is that 2 steps in one? If x is not in A union B, then it's not the case that x is in A or x is in B.
Yeah. But
I think that's the simplest.
well, I'm just saying you could do an intermediary step that goes not x is in A union B and split it, but it's the same thing.
Anyways, so now we have it like that. Now we distribute our not. So that becomes x is not in A and x is not in B. Right? Distributing the not x in A is x is not in A, not x in B is x is not in B. Switch your or to an and.
Yeah.
Okay? And then finally, if x is not in A, what does that mean? That means x is in A complement and x is in B complement. Then that means that x is in A complement intersect B complement, which I think is what we were trying to prove, hopefully. Yeah. Make sense there?
Yeah.
And so once again, the hard the proof is just distributing this negative, which you could see pretty well from just how this works. And then this one's the same way. You're just distributing a not over an or, and it's going to give you a not, or sorry, you're distributing a not over an and.
Maybe even more.
So not and is not or not, right? Okay, 25. A minus itself is just the empty set. That one's probably the hardest one to visualize. You'll get there. Okay, and then these next 3 are kind of weird ones. Rewriting A minus B. We'll start with Venn diagram pictures, and then if they don't make sense, we'll prove it. So we have A, and we have B. So here's A, here's B. Now remember, for 26, 27, 28, we're always talking about this space over here. A minus B, that's over here. And we're saying this is a different way of writing it, this is a different way of writing it, this is a different way of writing it. Okay? So let's go over each of these. So I say A minus A intersect B. So A minus A intersect B just leaves me the stuff over there. Does that one make intuitive sense? Alright, let's do the next one. A intersect A minus B. So take A minus B and now intersect it with A.
Oh, so now it's A. Oh, now it's A minus
It's still just A minus B.
Yeah.
Everything in A minus B is also in A. So A minus B intersected with A is still just A minus B.
Right.
Does that make intuitive sense?
Mm-hmm.
If it's in A and not in B, and it's in A, then it's in A and not in B.
Crazy.
Is another way to think about that. Does that make sense, or do we need to see it?
Makes sense.
Okay. 28. So if you take A, get rid of everything in B, and then get rid of everything in B again, you're left with the stuff over here.
Wow, crazy.
It's like taking a bite out of air.
Okay, so all those make sense?
Mm-hmm.
They might seem weird, but pretty intuitive. 29, if you do A minus B, so take A, get rid of everything in B, and then get rid of everything in A, you're left with nothing. Does that make sense what I'm saying?
Yeah.
Alright. And then A minus B union B is just A union B. Okay, so take A, get rid of everything in B, and then put in everything in B. And you're left with everything in A or B.
Why?
They're just ways of simplifying your expressions. I can't come up with one on the fly, but you could imagine that you're doing some, we'll call it set algebra,
Yes.
where you have A minus B union with B, and it would very much help to rewrite it like that. I mean, because you could have taken this, simplified to that, and then that, simplified to that.
Looking
I don't
at
know.
that at face value, it's actually not like, okay, that's very obvious.
Well, that's the thing about all these. When you look at them, it doesn't look obvious until you think about it for a second, then it's like,
Oh, yeah.
well, duh. Alright, so now this one. Take everything in A or B, and then get rid of everything in B. What are you left with? You're left with everything in A that's not in B.
Yeah. A.
So we have everything in A or B.
Yeah.
Now get rid of everything in B.
Right.
You're left with the stuff over here.
Yes.
Yep.
A minus B.
So we found 4 ways to write A minus B.
Yep. And then the author makes note, but it's not at all obvious to me, that to do an axiom, to get axioms for set theory, he said you could use the first 8 as axioms and then include this as an axiom.
First 8 what?
The first 8 properties we have listed there.
And you can build
So if you make those first 8 axioms and then include this as your 9th axiom, then he said that you could derive everything else from those things.
Really?
That's cool.
Can't we derive?
Yeah, were we just deriving them using logic and definitions?
Yeah.
Yeah, we were.
Oh, he's just saying.
It is not obvious to me how those axioms encode what we needed, because nowhere do they ever use the member symbol. So maybe I was misunderstanding what he was saying.
Do you assume the definitions as well?
Yeah, so he says, assuming the definitions for union, intersection, and subtraction. He just talked about the operations. So, that didn't make any sense to me. I'm pretty sure I must have been misunderstanding him, but I'm guessing none of you guys read it. So,
Shoot.
you can't really correct that for me. Because when you look at the axioms for set theory, those are not them. And it doesn't make sense that those are axioms. But that's what he claims. And maybe all he meant is that they can be used as axioms to prove the remainder of this stuff, and that they're not axioms for set theory in general. That's probably what he meant. So, that's what he says. If any of you want to try those, you can try those. But that's the end of the chapter. So now the question becomes for next week. I guess we don't need to record anymore. We're done covering material.